So let's begin. Okay, now before getting into the concept of local maxima and minima, just a couple of more types of questions I wanted to discuss. So, for example, we have something like this: y is equal to tan inverse of x, and we want to find out the derivative. Okay. Now, as some of you might have seen in advanced calculus type of references, that there is a direct formula for this, that differentiation of tan inverse x is given by the formula 1 upon 1 plus x square. But here we don't need to use this formula directly because we haven't learned it yet. Instead, what we can use is chain rule concept. So how to use chain rule? So y is equal to tan inverse x. First of all, what does this statement mean? This means that tan y is equal to x. Okay. So this function, this is the tan inverse function. Okay. So first of all, this should not be confused with this. This is 1 upon tan x, but this is tan inverse of x. So inverse trigonometric functions are like this. That if A is equal to sine inverse of B, it means that sine A is equal to B. If A is equal to cos inverse of B, it means that cos A is equal to B, and so on and so forth. So for example, you know that if A is equal to tan inverse of 3 by 4, that means that tan A is equal to 3 by 4, or equal to 37 degrees, or in general. So this is called the general solution of this. This is the general solution. Yes, Nishchay, you have a doubt, beta?
Sir, we can directly write it 180 and plus 37 degree, right?
Very
Because
good. We can write it as n pi plus 37. Very good. So this solution set can generally be written also in that way, because it is tan inverse. So anyway, you are familiar with the inverse trigonometric functions a little bit in mathematics, what they mean?
yes.
Right, people?
Yes.
Yes, sir.
Okay. So now let's see how we will differentiate this. So for differentiation, like instead of using the direct formula, we will use the chain rule. So how to differentiate this now? So coming back to this, how to differentiate to find dy by dx. Now we will differentiate both sides with respect to x. So differentiation with respect to x of tan y is on the other side, differentiation with respect to x of x. Now proceed by chain rule. Okay. So when you proceed by chain rule and solve the question fully, you will see that you will automatically come to this formula yourself. Okay. So just try these steps yourself. I will put it up in a moment. Okay. Just use chain rule on the left hand side, and right hand side is directly equal to 1.
So, sir, if tan y equals to x, that means after it's differentiated, it's also the same.
If tan y is equal to x, then see, differentiation of tan y with respect to x will become 1. That means you're understanding the point, no? Like think of tan y like a new quantity z. No, z is equal to x. So dz by dx is equal to 1. That is what it means, no, beta?
Okay, sir.
But now how will you differentiate tan y with respect to x? Tan y, if you think that it's a function of y and you want to differentiate it with respect to x, so you have to use chain rule. Are you following?
Yes, sir.
Yes, sir.
So just use the chain rule and see what step you will get.
Sir, sec square y into dy by dx is equal to 1.
Yes, very good. Okay, and sec square y you can use as that you can express in terms of tan y. No, you can use identity that sec square is equal to 1 plus tan square.
Yes, sir.
Right, this is session number 7 for us, right? Okay, so let's see. So the use of chain rule now will become like this, that differentiation of tan y with respect to y into dy by dx. On the other side, that's equal to 1. Okay, this is our chain rule step. So sec square y dy by dx is equal to 1. So dy by dx is 1 upon sec square y. That is 1 upon 1 plus tan square y. Now why I need to do this step? Because I have expressed dy by dx in terms of y. I need to express it in terms of x. So I need to again resubstitute y in terms of x. So to resubstitute, I need to use this, that tan y is equal to x. That's how this is becoming. That's how I get this formula now. So like this, any inverse trigonometric functions differentiation, though there is a list of formulae for it, but we can achieve it by just using this method of chain rule. Okay, people, so hope this is clear.
Yes, sir.
Okay, so you can, for example, use a similar method to show that differentiation of sine inverse x is given by the formula 1 upon square root of 1 minus x square. So try this yourself later. We'll discuss again. Now let's move on to the concept of maxima and minima of a function. Yes, sorry, beta. Yeah. Yeah, I'll send you the notes. So when you're reviewing today's notes, you can just try this yourself. Yes, Nishya.
Sir, after differentiating, I got 1 by cos y. But if we write cos y as under root cos square y, we are ignoring the negative roots, right? Like cos
Yeah.
can be negative also. So this
Yes.
formula is not exactly correct, right?
No, so the interpretation of the formula beta will come in terms of this thing. Na? See, if you think of the graph now of sine inverse x, okay, if you look at the slope at different places, you'll understand how this relates. Okay, because remember that when we use, for example, na, y is equal to sine inverse x. Now, if I say, for example, sine inverse of half, okay, that can be pi by 6, that can be 5 pi by 6, or in general, it can be 2n pi, okay, plus pi by 6, or 2n plus 1 pi minus pi by 6. Huh?
Yes.
So in general, in any way to find the slope of the tangent, we have to break the domain into smaller sets. You understanding? No?
Yes, sir.
So here the formula that we'll get for the slope of the tangent, no, it will only be applicable for the first quadrant.
Okay, sir.
Yes, Janvi, you understanding the point?
So what we're saying is, so sine y is equal to x. It means, so for one value of x, I can have multiple values of y, right?
Yeah, exactly. So that means when we are thinking of it in terms of function, no, we are restricting the domain so that that doesn't happen.
Achha. Okay, sir.
Got the point? No? Okay.
Yes.
So this is like, more like we are thinking of differentiation as a tool of finding slope of tangent. So even if I have a expression which is not a function, like y square is equal to x square, but at different points on the function's graph, sorry, different points on the expression's graph, I can find the slope of the tangent now. Yes,
Yes,
Nishya?
sir.
Sir, so this formula is applicable only for the first quadrant, right?
Yes.
Till 90 degree.
Yes, and we have to interpret it accordingly for the different quadrants.
So if it suppose the value is minus half,
Hmm.
then what will we do in that case? What will be the sign inverse? Because then it is negative, so it will extend to the
So
first
see,
quadrant.
sine inverse of minus half, na? If I take sine inverse of minus half is equal to something, let's say A. Okay. So that means A is in which quadrant? Is either in third or fourth quadrant?
Yes.
Okay. So I'll have to interpret A accordingly. That A is the same thing as, if it is in third quadrant, it is what? Pi plus sine inverse of half.
Yes.
Okay. Or if it is in fourth quadrant, it is minus of sine inverse of half, or 2 pi minus sine inverse of half.
Yes, sir.
And then accordingly I have to interpret.
So means we will get a positive value or the value in a first quadrant. Then accordingly, if it is negative, we have to relate it with the third and fourth.
Yes. So
quadrant,
first of all, you'll understand this thing, that if I write this as a function, if I think of this like a function, sorry, y is equal to sine inverse A, sine inverse x, then I'm talking about a limited domain for the first quadrant. Okay. I'm talking about the domain that x is between 0 and 1.
Yes.
You understanding? Or if I think of the like so for example here, if I take x is greater than equal to 0, less than equal to 1 as the domain, then the range of the function is becoming between 0 and 90 degrees, or between 0 and pi by 2. But for example, if I interpret the domain as between -1 and +1, okay, then I can interpret the range as between -90 degrees and +90 degrees.
Yes.
Okay, so that is only in like the first set of solutions. You understand, no? Because actually any value will have multiple solutions. No? In fact,
Yes.
for it will have infinite solutions like that. So the inverse trigonometric functions have to be interpreted like that in restricted domain.
Okay, sir. So we
Okay.
will get a value in the first quadrant, then we have to relate it.
Yes, then you have to relate it that way. Okay. So that is why like this comes under the subject of slightly more advanced calculus. So we need not get into it too much right now. But if you see a question where there is some inverse trigonometric function, this is how you will interpret it. Okay.
Yes.
Now let's talk about maxima and minima of functions. So notice I'm not using the term local maxima and minima to begin with, because we will discuss maxima and minima itself in general. So there are two types of maxima and minima we talk about. We talk about global maxima and we talk about local maxima and minima. So for example, suppose we are talking about a function like this, y is equal to x square. Now if you look at the graph of the function, and I have not given anything specific about the domain. So if nothing specific is given about the values of x, that means I should take all values of x for which y is real, which is nothing but all real values of x. Okay. So here, if I take x belonging to -infinity to infinity, then you know the graph of the function will be such that it's roughly speaking something like this. So this will imply that y belongs to the set of 0 close to open infinity. So in this case, we will see that for this domain, because in the example, no specific domain was given, we will take the largest possible domain of x, which is all real numbers. So we will see that overall, the maximum possible value of y is tending to infinity. It's tending to plus infinity. So we will say that the global maxima is equal to +1. Okay. And we can see the minimum possible value of y is equal to 0. So we will say that the global minima is equal to 0. So you can see that y ranges between the global minima to the global maxima. Okay. So
Sir,
what is the yes?
sir, how is the global maxima +1?
My mistake. It is plus infinity. So it's going to infinity, right? And the global minima is equal to 0. So what is global maxima and global minima? Global maxima and minima are the overall maximum and minimum values of the output of the function. So if the function is, so what y is equal to fx, okay, we say that global maxima equals to the maximum value of y for all possible values of x. Okay. or in better mathematical language, we will say for the given domain of X. And similarly, global minima will become the overall minimum, okay, or the minimum possible value of Y for all possible values of X, or in other words, the given domain. Again, for given domain of X. Domain is basically the set of values of X that we take for a function. So if a particular problem or a particular situation doesn't specify what the domain is, like over here in the example given, I had not specified what the values of X are, then we are supposed to take the largest possible set of values of X for which we get real values of Y. If there is a specific domain given, then obviously we take that specific domain. Okay. So for example, tell me if I have a function y is equal to 1 plus 4 sine x plus pi by 3. Okay. Can you tell me global maxima and minima?
Sir, 5 and
Yes, very good. Global maxima is 5,
3.
Minus
Minus
3.
3.
minus 3. Very good. Okay. So you can see here what is happening is that in the particular question that we have taken, there is no there is no restriction given in the question for X. Okay. So no specific domain is mentioned. So first step, that means that we will take largest possible domain. In other words, X can take any value for which Y is defined or for which Y is real. So in this case, you can see that X belongs to the set of minus infinity to plus infinity. But now we know that for this domain, sine of X plus pi by 3, okay, is such that we can think of this like a sine theta, where theta is going from minus infinity to plus infinity. So that means sine theta is between plus 1 and minus 1. Or in other words, sine of X plus pi by 3 is between minus 1 and plus 1. So if I see the overall largest set of values of X possible from minus to plus infinity, this term, this sine of X plus pi by 3 term can never become less than minus 1 and can never be greater than plus 1. So by just applying the concept of inequality, we can see that Y can never be greater than 1 plus 4 times plus 1, and it can never be less than 1 plus 4 times minus 1. So Y ranges between minus 3 plus 5. So that means ultimately what that means here is that X belonging to the set of minus infinity to plus infinity, Y belongs to the set closed interval minus 3 to closed interval 5, inclusive of minus 3 and 5. So that, or in other words, we say that this is the range of the function. Okay, the values of Y that it takes for a given domain, this is called the range of the function. Whereas here the values of X that are taken, this is called the domain of the function. Okay. So another way of saying it is that the range of the function always ranges between global minima and global maxima. Therefore, global maxima equals to +5 and global minima equals to -3. You can write this as 5 also. You don't have to strictly write the algebraic sign. But so another way of expressing global maxima and global minima as definitions is that it is just the endpoints of the range. That is, whatever set of values the y takes in the function or the dependent variable takes, okay, it is the upper and lower limit of that. So this is the specific term global maxima and global minima. So as you can see that it is not really defined in terms of anything to do with calculus. Global maxima and minima is not really defined with anything to do with calculus. Now the thing is that if we have a restricted domain, then we have to be a little bit more careful about how the global maxima and minima are defined. Okay. So first of all, hope this process was clear to all of you. Anybody has a doubt in this, you can please ask me. Okay. Let's do a quick couple of questions based on this. Okay. So we have, suppose y is equal to 1 plus x cube and x belongs to the set -5 to 5. So this is what is called a function with a given restricted domain. An example of a function with a specified restricted domain. So if the domain is restricted, that means we cannot take values of x outside of the given domain. Okay. Now find the global maxima and minima. Just tell me the answers to this quickly. Come. Okay. Yes, very good. Yes, Nishchay, Piyush, Anirudh, Janvi, Mansi, Aparna, Abhinav, Jairaj, all of you got this correct. Okay. So you will see here that the global maxima will be 126 and the global minima will be minus of 124. So you will see that y will belong to the set of this for x belonging to the set of.
But sir, if it's a restricted domain, then how is it global?
No, because see, restricted domain just means that when we think of the graph of the function, we are not supposed to draw it before this point or beyond that point. You understanding my point?
Okay.
See, when the domain is restricted, no, the range also becomes restricted. You can think of it in another way also.
Yes, sir.
So now what is the definition of global maxima and minima? It is just the endpoints of the range. The upper limit of the range is global maxima. The lower point of the range is global minima. Following now, beta? Okay. So the easiest way we could have analyzed this function is we could have seen that x cube is a term, a function x cube is what we call, it is an increasing function for all values of x. Because we are familiar with the graph of x cube. We think of the function y is equal to x cube. We have already seen the graph of this before, that it goes slightly and it goes like this. Okay. So therefore, what does the, this is also an increasing function for all x. Yes, Sanvi, you have a question, beta?
Sir, won't you put that curly bracket for y belonging to, because then it becomes everything in the middle also?
No, curly bracket beta is for specific values.
So isn't the specific value?
No, this is like the range. No? So what this means to say is that y belongs to all real numbers in between minus 124 and 126, inclusive of this, for x belonging to all real numbers which are like this. No? So it's
Oh,
also
okay.
taking, understood the point? Okay.
Yes, sir.
So another way of writing this above statement is that if I take a restricted domain where x is in between minus 5 and 5, inclusive of minus 5 and 5, then y will become restricted in between minus 124 and 126, inclusive of all the terms.
Got
So
it,
from
sir.
this, understood? No? Okay. So I can see that therefore minimum value of y is when x is minimum. That is for the lower point of the domain, and maximum value is for maximum value of x. So that's how I'm logically understanding. Okay. But now obviously, as you can understand, for some functions it will not go, it's not going to be so simple, you know, how to find the global maxima and minimum. So again, we will come into the analysis of calculus a little bit, how it can make things little easier. Okay. So for example, now suppose I have a function y is equal to x cube minus 3x plus 2. Okay. And I take a restricted domain that x is, let's say, in between 0 and 10. Okay. Now I ask you, what is the global maxima and minima for the given and for the given domain? Immediately you understand that it's not such a simple problem, because this is not going to be a, you know, monotonic kind of graph. You will see here that x cube minus 3x plus 2 is not a function that increases all the way or decreases all the way. It has a certain situation where 3x dominates over x cube. So it is in fact a decreasing function. And it has certain values of x for which x cube dominates over 3x. So it's increasing in nature. So then we have to see that we have to take the help of calculus. So we need the help of calculus to get some idea about the graph.
Second derivative check.
Actually, even first derivative will do, because what we need to understand is that on the number line between 0 and 10, specifically for x, what is the behavior of y? Okay, suppose y is just increasing all the way, then f of 0 will become my global minima and f of 10 will become my global maxima. If something like this is happening, that suppose the function is first decreasing and then increasing, okay, then what we need to do is we'll have to find up to where it is decreasing, and after that point how it is increasing, and we have to then compare. Okay, suppose the function is changing behavior more than one time in between 0 and 10, like it's first increasing, then decreasing, then increasing, then we all need to check. So we need to visualize the graph of the function between 0 and 10. Okay, so we need to take the help of calculus to get some kind of idea or to visualize the graph of the function for at least this restricted domain. If not the whole thing, then at least for the restricted domain, we need the help of calculus. Now, what kind of help of calculus we can see? Behavior of the function. Behavior of a function from the fact that the function increases for derivative to be negative, sorry, to be positive. Okay, and the function decreases for derivative be negative. This thing we need to take the help of. Okay, so let's start with this. For this given function, x cube minus 3x plus 2, let's find out that in between 0 and 10. Okay, for this restricted domain, is there any subset for which y is increasing? And similarly, is there any subset for which y is decreasing? Or is the function what we call monotonic in behavior? Monotonic means that it has one type of behavior. It either is increasing all the way or it's decreasing all the way. Okay, so can you all analyze this thing to start with? That between 0 and 10, yes, people, just a minute. Yeah, Nishchay beta.
Yes,
Yeah.
sir.
Yeah,
Here you have written f of x is increasing for f prime x greater than 0. But this is not always true, that if we go in negative cases, then the graph will increase, right?
No. How do you mean that, beta? See, what is f prime x? It is the slope of the tangent, no?
Yes, sir.
So if the slope of the tangent is negative, that means irrespective of whether your values of x are on the left side of 0 or on the right side of 0, the graph shape is what it is decreasing. No?
Achha,
Understood the point? No?
Yes.
Like you think of the graph of y is equal to x square only for negative values of x. You know? So as your x goes from -4 to -3, your y is going from 16 to 9. No?
Yes, sir.
Like that. Yeah. Somebody else had a doubt? Okay, very good. Janvi, I will come to your question about what would happen if there were open brackets given. Okay.
That means if f prime x is negative, then
Yes.
The function will be decreasing, right?
Yes. Okay.
Constantly.
So f prime x is negative will be for some interval of x. No? So that means in that interval of x, as we are moving on the positive side of the x-axis, the graph of the function will be going down. That is the meaning of decreasing function, right? Yeah, Dhruv, I'm coming to your question. No, Dhruv, your interpretation of local maxima and minima is not correct at the moment. Okay, I will explain local maxima and minima. Global maxima and minima is what you have suggested, that it is the overall maximum and minimum possible value of y for all possible values of x, or what we call the domain of the function. Now, domain of the function has two interpretations. If no specific domain is given, then we should take what is called the natural domain of x. That is the largest possible set of x for which y is defined. Whereas if, like in the question given over here, the question itself or the situation gives us a restricted domain, then the domain has to be taken accordingly. So for example, in this question, if I had not mentioned 0 to 10, then we would have taken x as the set of all real numbers, because y is defined for the set of all real numbers. Yes, Nishchay?
So means global maxima and minima, sir, can we visualize if we take a particular domain of x, then in that fixed domain, the global maxima will be the local maxima and the global minima will be the local minima. Is it true?
Not always. In certain cases, yes.
So why?
I'll explain to you. Okay, I'll explain to you. In fact, when we come to the graph of this function only, I'll show you how that happens. Okay. Yeah, Ibrahim, you got the first thing correct. Okay. Just check the values for which f prime x is positive once. To answer your question, okay, here we are talking about functions such that the output of the function is a real number. Okay, we are not talking about functions of complex numbers. Okay, so imaginary numbers are not included in this. The definition of functions is for us is such that y is equal to fx. Only such values of x should be taken in general where y is real.
Okay, sir. Thank you.
Okay, so let's start with this. So given function is x cube minus 3x plus 2, but for a restricted domain 0 to 10. So first thing, let's analyze that what is the derivative of the function. It's 3x square minus 3. Okay. So it is 3 into x minus 1 into x plus 1. So in general, we can see that, you know, of course, here we'll take a restricted domain. So this is the behavior of x minus 1. This is the behavior of x plus 1. Oh, sorry, this is the so x plus 1 is negative for x less than minus 1, and x minus 1 is negative for x less than 1. So if I had taken an unlimited domain, then the derivative would be okay, positive here, negative here, and positive here. So now I have taken a restricted domain. So x I'm taking only between 0 and 10. So between 0 and 10, you can see I have a critical point of only plus 1. So f prime x is negative up to here, and so in my restricted domain, this is what I can see. So about the function, therefore, what I can say is that the function is decreasing in this region and increasing in this region. So without drawing an exact graph also, I can say that when I'm taking the specific values of x between 0 and 10, I need to pay attention to the point x equal to 1, because the behavior of the function is changing in between. Okay. So what I need to analyze f of 0, and how much is that? It's plus 2. I need to analyze f of 1, and how much that is?
0.
0. Very good. Okay. And I need to analyze f of 10, and how much that is?
972.
972. Okay. So it's this type of a function. I'm not worried about the rest of the graph, but just looking at this part, it will probably be something like this. Okay. Not drawn to scale, because obviously 972 is a very large number. Okay. But this point over here should have coordinates of 10, 972. Okay. This point should have coordinates of 1, 0. And this point should have coordinates of 0, 2. Okay. So this is clearly showing me, this graph is clearly showing me, without getting into second derivative, without getting into turning point and all that, just by understanding the behavior of the function in this limited part of the domain, just between 0 and 10, looking at the limited part of the domain, I can see that for x belonging to 0 to 10, I can see that y belongs to 0 to 972. Okay. So I can see that global minimum or global minima of the function is equal to 0, and it occurs at x equal to 1. Okay. Now this is one more thing. You should not confuse between the value of x and the value of y. Remember, maxima and minima always refers to what's happening to your y coordinate. So my y coordinate, the minimum value it's coming to, that one is 0. So the value of the global minima is nothing but the value of the minimum y coordinate, okay, or the lower limit of the range. The range is going from global minimum to global maximum. Okay. So this is called the range of the function. So we will never say that the global minimum is equal to 1. That would be wrong, because y is coming below Okay, we'll say global minima's value is the lower limit of the range, which is 0, but it's occurring at the point x equal to 1. That is the significance of x equal to 1, that it is the point in the domain for which the range is coming to the minimum value or the global minimum. Okay. Whereas the global maxima, we can see over here, is equal to 972, which by the way occurs at x equal to 10. Okay. Now suppose I had taken an open interval, Janvi, to answer your question, that x belongs to open interval 0 to 10, so greater than 0 and less than 10. Then we would have said that the global maxima tends to 972 as x tends to 10, because x will not take the exact value of 10, so y will not take the exact value of 972. So if though this had been open interval, then y would also have open interval. Sorry, my mistake. Then y would have lower limit with a closed interval, but upper limit with an open interval. So my global minima would have been exactly equal to 0 because x takes the value of 1. But my global maxima would have been tending to 972 as x tends to 10. Okay, so hope this point is also clear. Yes, Ibrahim, your thing was right. So hope it's now becoming apparent how calculus is useful in finding the global maxima and minima also function. I have not even come to local maxima and minima yet. Yes, Janvi, you have a question, beta?
So there's one shortened method, sir, to find the minima. So in the graph, we can see at +1, so it's the function is increasing from negative to positive, and it's 0. The first we
But
put
how you can guess that without calculus? You tell me, beta. Just looking at the function x cube minus 3x plus 1 plus 2, can we guess that?
no, sir, just skipping the graph. So before
Ah.
that, only 3x minus 1 and x plus
Just that you can do. You just need to see these 3 points. You understanding my point?
yes, sir.
Matlab, you can skip the graph part. This was not necessary. Just this number line thing you have seen, that it's decreasing from 0 to 1 and then increasing from 1 to 10. So you just need to check at these points. What are the values for the maxima? Minima anyway, you will know is occurring at 1.
So if in any case there are more than one critical point between the given domain of X,
then it
so
becomes
do
more.
we check for there also?
Yes,
Like,
then we need to check for that also.
okay, sir.
Like for example, this same question, if I had given the domain from let's say -2 to +2, then something more interesting would be happening in that domain. If I had taken from -2 to +2, then the function is changing behavior twice. The function would be increasing here, okay, then decreasing here, then increasing here. Okay. So then I could have had the global minimum at -2. I could have had the global minimum at 1. Okay. I could have had the global maxima at -1 or 2, one of these 2 points. So I need to check all these things. Right? This was the point you were making, no, beta?
Yes, sir.
Yeah. So we'll come to examples and we'll understand that. Okay. But you can see that how the whole concept of differentiation, and the values of derivative of a function, that in which subset of the domain the derivative is positive and which subset of the domain the derivative is negative, how it's going to help us in situations like this, right? So all we have to do is we have to understand that for the given domain, which is 0 to 10, is the function monotonous? No, because you can see this is changing behavior. So if it is non-monotonous, then we need to divide the domain into subsets where it is increasing or decreasing. So now having understood this definition of, yes.
Sir, in the last graph, the local minima and the global minima are the same, right?
Are coinciding, yes. Yes, that's correct. Okay. So that can happen, but sometimes that need not happen also. Okay. And something very strange can also happen. So first let me define local maxima and minima. But sometimes it can so happen that your local minima is a global maxima. or it can even happen that your local minima is actually greater than your local maxima. So before that, let's understand the what is the concept of local maxima and minima. So local maxima and minima are really something which are, like, if you look at the simplest way of logically understanding them, it is nothing but a reference to the graph. It's better to express it in terms of the visualization of the graph of the function rather than a word definition. We'll give it a word definition also, but it's really all about the behavior of the graph. So suppose we take some imaginary function, some hypothetical function whose graph is like this. Some function y is equal to fx. In fact, something like this. Now, for example, there must be some point A over here, let's say, some point B over here, and some point C over here, where the function is having this kind of behavior, that exactly at those points, the tangent is horizontal. But the behavior of the function is changing from increasing to decreasing as you go across the point A. The behavior of the function is changing from decreasing to increasing as you go across the point B. And similarly across the point C. Okay, so what we can see is that for the above function, f prime x is equal to 0 at x equal to A, x equal to B, and x equal to C. Okay. And another thing we can see is that if you look at what is called the immediate neighborhood of the point E, so now it again comes down to that definition of limit delta x tending to 0. So if I compare 3 points, one at A minus delta x and A plus delta x, then out of these 3 points, f of A is maximum. Similarly, if I look at the immediate neighborhood of B, out of 3 points, one on the left side of B and one on the right side of B, and B itself, you can see B is the smaller of the 3. And similarly, if I look at the point C, the in-between point is having the maximum value. So if that is another feature of these 3 points, okay, if the slope of the tangent is 0 at that point, okay, so that this basically means that slope of a tangent at x equal to A, x equal to B, and x equal to C equals to 0. So that's the first thing you're noting. Now the second thing you can see is that at x equal to A, the behavior of the function is changing from f prime x is equal to a negative value at x equal to A minus delta x tending to 0, to f prime x is a positive quantity at x equal to A plus delta x, but delta x is tending to 0. Okay. Here delta x is a positive quantity. Delta x is a quantity which is tending to 0 but positive.
Sir, can you give us 2 minutes to note it down?
Yes. Okay. So now the second point I've just made about the point x equal to A. Now similarly, we'll make an observation like that about the point B and C also. So we'll see that C has the same behavior as A as far as the second point is concerned, but B has the opposite behavior. In case of B, just before B, the derivative is
Sir, in case of A, it should change from positive to
positive.
negative, right?
Yeah, it's changing
Yes,
from
sir.
positive to negative. Whereas in case of B, it is changing from negative to positive. Okay, so you can go ahead and note down this point, and then we will see the same behavior we'll see at the other 2 points also, B and C, as far as the second point is concerned, that how the slope of the tangent is changing.
Done, sir.
Okay, done now. Okay. Now, similarly, if you observe about B, what is happening at x equal to B, behavior is changing from f prime x being negative at x equal to B minus delta x to f prime x being positive at x equal to B plus delta x. Here delta x is tending to 0, but it's a positive value. Okay, so when we look at a particular point along with 2 points like this, it is called the immediate neighborhood of a point. Okay, so x equal to a, or we can say like this, that for a point x equal to a, x equal to a minus delta x tending to 0 is called the left hand limit of x equal to a. So this point is just like immediately to the left of a. Yes, Nishchay.
Sir, can you please explain this left-hand limit again?
Yeah, I'm explaining that only. Okay, just let's write down the definition plus. Okay, first. Okay, and x equal to a plus delta x tending to 0 and a positive quantity. This is called the right hand limit of x equal to a. So this is a point which is immediately to the right of a. Okay, so we are just talking about values of x. So visualize the number line. Okay, so if on the number line we have a particular point a, okay, then a point just to the left of this and a point just to the right of this. These 2 points are a minus delta x and a plus delta x. So that one is just to the left, so it is called the left hand limit, and a plus delta x is just to the right, so it is called the right hand limit. And when we take delta x tending to 0, okay, it is like we are talking about almost 3 consecutive points. Understanding, like we had discussed about in instantaneous rate of change versus average rate of change, you know. Okay, now it's clear, Nishya?
Yes, sir.
So this is called the immediate neighborhood of a. So x belonging to, you're defining delta x as tending to 0. So in any case, we have to take the open interval.
Sir, but we can take any other point other than the left-hand limit or the right-hand limit just before a, right? Like
For what?
for that particular range, for that particular domain, because at that point, the slope will always be. The
No,
slope
so
will
that is the
always be
point.
positive.
Like to define local maxima and minima. No? See, it can always happen like this, no? That you have a situation like this. Okay. Now you can see here, if this is my point x equal to a. Okay. So there is some point before a also, no, at which the slope is positive.
Yes.
So if I take general value of delta x, no, instead of taking delta x tending to 0, then I might take delta x so large that I'm covering this distance.
Yes, sir. I got it.
So now you can see that between this point and this point, or between this point and let's say this point, now the behavior of the function is not changing. Now here also slope is positive, here also slope is positive. But how I can be sure that I don't make the mistake of taking 2 such points? I take a point over here and a point over here. So I can bring these points as close as I like to a. Okay, for the definition to remain consistent.
Yes, I got it.
So if I have a very rapidly changing function, okay, then I have to do this. Okay. Now, obviously, most natural functions are not so rapidly changing. So I need not take delta x tending to 0. I can just say that delta x is a small value. Okay. But yes, if I have to make a general rule out of it, I have to make delta x as small as possible. So that is tending to 0. Okay. So x belonging to this interval a minus delta x to a plus delta x, where delta x is a quantity which is positive and tending to 0. Okay. So this is a set of values, okay, because I've written it as an interval. This is called the immediate neighborhood. It's called the immediate neighborhood of A. So coming back to the graph of the function, what we could have observed there is that the value of y is maximum in the immediate neighborhood of A. It is not overall maximum maybe, okay, because our function was something like this. Okay. But what we saw is that if you look at the immediate neighborhood of A, just before x equal to A and just after x equal to A, okay, then the function is peaking at that point. Similarly, if I look at the immediate neighborhood of B, the function is having a minima at that point. Okay. It's not the global minima because there's some point over here where the value of the function is becoming less than B, less than f of B. Okay. And similarly, if you look at the point C, in this case, it may be the global maxima, but it is also a local maxima. So we will define this as a point of local maxima. And a function can have any number of local maximas. Whereas this one is a point of local minima. Okay. So now we have this kind of a definition based on local neighborhood. Yes, Nishchay.
Sir, so out of a total number of local maximas, there is only one global maxima, right?
Yeah, and the other interesting thing is, see, your global maxima may not be a local maxima. Like you visualize a cubic function, it's like this.
Yes.
You understanding, no? Like if we had seen that function that we've taken, the x cube minus 3x plus 2, that one only, in the overall domain for all real numbers, then y would be tending to infinity as x tends to infinity.
Yes.
So our global maxima is tending to infinity, but there the behavior of the function is not changing like this. It's monotonic by the time you go there.
Yes, I got it.
So global maxima and minima may not have any overlap with local maxima or minima. On the other hand, it may also. Like the easiest example is any periodic function like sine x or cos x. The global maxima is equal to +1 and it occurs at infinite values of x. And they are all also points of local maxima. Okay. So now we can define local maxima and minima, okay, from a graphical point of view. A local maxima, you just remember, it's like a temporary peak. Okay, or within a neighborhood of a certain point, if the value of the function has a maximum at that given point, so within the neighborhood of A, if fa is maximum, then it's a local maximum. Within the neighborhood of the point x equal to b, if f of b is minimum, then it's a local minimum. So local maxima is the value of a function at a point. Suppose we take that point is equal to x equal to a or x equal to c, such that it is a maximum value in the immediate neighborhood. of that point. Okay. So in other words, we will say if f of a is greater than f of a plus minus delta x tends to 0, then that means f of a is the local maxima for the function fx, or same occurs to the point C. So now you can see that we have a mathematical definition of local maxima. This is the condition for local maxima. Now I don't even need to say that delta x has to be positive. It can be a negative value also, because I've taken plus minus. Yes, Nishchay.
So we can say that for x belonging to a minus delta x to a plus delta x, the value of a will have the maximum value. So it is
Yes,
the
absolutely. That's what we can say. No? So in that small neighborhood from a minus delta x to a plus delta x, your function is peaking at that point. It has the maxima. So that is the local maxima for the overall domain. Okay? So this is the condition for local maxima of fx at the point x equal to e. Okay. And in this case, it applies to the point C also. So in everyday language, we can say that local maxima is the value of the function at a point where it peaks, where there's a temporary peak. It may not be the biggest peak. It may not be the biggest value. It may not be the global maxima. Okay, but it's at a peak. So it is a peak point. The graph of y is equal to fx.
So a plus delta x is not the local maxima. It's
No. In fact, see, the term local maxima is used for what? The y coordinate. So its value is fa. F of a, that is the value of the y coordinate at that in between point where it's peaking exactly. That is the value of the local maxima. And where the local maxima is occurring, it's occurring at x equal to a. You understanding the point, Bhattacharya? So for example, for sin x, the local maxima is y equal to 1, y equal to sin x. The local maxima is x equal to 1. And where the local maxima occurs, it occurs at infinite points like pi by 2, 5 pi by 2, and so on and so forth.
so then what was the use of doing that neighborhood, immediate neighborhood?
Because the function might be very rapidly changing.
Okay, sir.
Understood the point? So we
So
need to compare 3 consecutive points. One just before a, one just after a, and if the middle point is where it peaks, then that is the point of local maximum.
okay, sir. So one more thing.
Yes.
If you're suppose you take x equal to b on that graph, how can you say that both the left hand limit and the right hand limit are minus and plus? How is it not both b plus delta x? Because it's like a plateau kind of shape. Then both the points on the
No, so
right
the
and the left.
thing is better, even if you zoom on to the plateau also, no, there must be some particular point where the tangent is flat. And before that point, the tangent is, because it's a natural curve, no? You understanding the point, no? A natural curve will never, when you zoom into the natural curve, no, it will never have a shape like this, that it will never be a shape like this that become like this. Okay. And it was curving before this. It won't be like this. It will always be like this. It will be always like this. So there's some particular point at which the tangent is 0. But any point even just before this will have a slight bend. Any point after this will have a slight bend. There's only one particular point where the tangent is horizontal. That is the theory of calculus about curves. You understanding the point now?
No, sir, I was saying the neighborhood points. How do you know that one is minus delta x and one is plus delta x?
No, because that is the definition of neighborhood, no? That before to after.
Okay, sir.
What my point? No? B
Yes.
has to be the in-between point, no? Or A has to be the in-between point. If we are talking about the immediate neighborhood of the point x equal to 1, that means we have to go from the point just before x equal to 1 to the point just after x equal to 1.
Yes, sir.
Understood the point? Okay.
I was getting confused as I was taking the value of x as y. So I was saying, how does the
Yeah. Understood. So now when I'm talking about neighborhood of x equal to b, now I'm talking about on the horizontal number line, no?
Yes,
Right?
sir.
Okay. So similarly, the definition of local minima becomes just the reverse of this. If at a given point, the value reaches a temporary dip instead of a peak, okay, then this inequality will just be reversed. Rest, everything will remain the same. So local minima of a function so what is it defined as? It is defined as the value of a function at a point, let's say x equal to b, such that fb is the minimum value in the immediate neighborhood of x equal to b. So mathematically, we will say that if f of b is less than, not even equal to, but less than f at either plus or minus of delta x. Okay, that means I'm taking three consecutive numbers on the number line and the middle number is b. Okay, so on the x-axis, I'm taking three consecutive points and the middle one, which is x equal to b, has the minimum of the 3 points value. That means the function fx has okay. And what is the value of the local minimum? It is the value of the function. So that means this is that type of point where the function tips. The graph of the function So now, particularly for finding the point of local maxima and minima, calculus is what helps us. Okay, because as you can see from the graph above, the slope of tangent is 0 at both such points, local maxima as well as local minima. So collectively, they are called turning points. Yes, Nishchay.
So can you give an example, sir, where local maxima is global minima and the local minima is global maxima as you were talking about?
Sorry, an example where local minima is?
So where, yes, sir, global maxima.
But there are some strange kind of graphs where these kind of things happen. Like, we were talking about, remember I gave you an example of a question, y is equal to x plus 1 by x.
Yes, sir.
I just given to analyze the the increasing and decreasing. When we look at the overall graph of the function, it's something like this. Okay. So not. So I will take this example again. Specifically, I had given this example then also so that later when we come to this now. So you can see at +1, it has a local minima of 1. Okay. And at -1, it has a local maxima of -1. Now this is the overall domain. Here I'm taking x belonging to the set of all real numbers other than 0. Okay. But if I take a restricted domain, then you will see something very interesting. But in any case, you can see that here, this is the local minima. The local minima has the value +1, and the local maxima has the value -1.
Yes.
So we'll come back to this, don't worry. But you know, these are very particular type of functions. In general, this doesn't really happen. The general shape of the graph of most functions is more like this one that I had drawn, you know, something like this.
So
And of
means
course, there are many
magnitude wise
functions.
it will not change, right?
Yes.
Magnitude wise it will not change.
Matlab,
Although
if you at
it's in
least
the
look at,
negative.
if you look at a series of turning points one after the other, they'll always alternate between maxima, minima, maxima, minima. Okay. Yes, Nishchay.
Sir, so in the third quadrant, sir, where we are having a local maxima, so it is our global minima. So in that case, sir, that
In
is in
which
the
quadrant,
third,
beta? I didn't understand. Which function you're talking about again?
sir, x plus 1 by x. Sir, so in that case, if sir, in that case, magnitude wise, it is still the maxima. However, if we because it is in the third quadrant, it has a negative value, and hence it is having a minimum value, right? Therefore, it is the global minima, right?
Now, global minimum depends on what we've taken the domain as. Na?
Sir, if I'm considering minus infinity to infinity, then it will be
Then
minus
global
infinity.
minima is tending to negative infinity, na beta?
Yes, sir.
Understanding, na? So yeah, things become quite interesting and complex, na, in situations like that.
Yes, sir.
Okay, so definition of local maxima and minima is clear, I hope. Okay, from this. Okay. Now, for any given function, okay, dy by dx or f prime x equals to 0 at all points that are either a local maxima or like a peak kind of point, or a local minima, that is a dip point. So collectively, values of x for which f prime x is equal to 0 are called turning points. The logic of this name is that the behavior of the function is turning. It is changing from increasing to decreasing or decreasing to increasing. Okay. So again, if you visualize a general graph, there are n number of points where the behavior of the function is changing. These are all turning points. They all because the slope of the tangent at all these points is going to be 0. So this is the common property that points of local maxima and local minima have, that the value of the derivative of the function is 0 at both these type of points, local maxima as well as local minima. So collectively, these points are called turning points. So in other words, you can say a turning point is either a local maxima or a local minima.
So then in a straight horizontal line, so what are the turning points?
You can say in that sense there are infinite turning points. No? A straight horizontal line or a constant function is just a collection of infinite turning points consecutively drawn.
Sir, I did not get it.
You did not get what, beta?
So this statement which you gave just now.
The straight horizontal line.
Yes, sir. Which
So straight horizontal line is an exceptional function, no? That in the entire domain, at each and every point, the derivative is 0.
yes, sir.
So derivative 0 को हमने कैसे define किया, that at any point where the derivative is 0, it's defined as a turning point.
तब समझ.
Now next we will see the difference between local maxima and minima. Okay. So the common point between local maxima and minima is at both the points the derivative is 0. But what is different about them? So if you look at a local maxima point, at that particular point, we draw the tangent, it has slope equal to 0. Now I'm drawing the next point with a bit of gap, but we will imagine that this delta x is made smaller and smaller till it tends to 0. So if I draw at x equal to a minus delta x, if I draw the tangent, I can see it is having a positive slope. And if I draw a point after this, you can see that it is having a negative slope. So what is happening? At a local maxima, okay, f prime x is positive at x f prime x is 0 and f prime x is negative. So in other words, what we can see is that f prime x has a decreasing nature. In the neighborhood of x equal to e. Okay. So at a local maxima point, this is what happens. The derivative is 0, but it has a decreasing nature. So in other words, the second derivative at x equal to a should be how much? It should be negative. Okay. So at any local maxima point, two things is happening. Derivative of the function at that point is equal to 0. And second derivative of the function at that point should be what type? It should be negative.
Sir, I didn't understand how is it negative, the double derivative.
Because see the value of the derivative, how it is changing. It is changing from positive to 0 to negative.
Yes.
So its own nature is what? its own nature there is that it's decreasing.
Acha, yes,
So
understood.
if you think of, first think of the graph of y is equal to fx. Okay. So if the graph of y is equal to fx is like this at the point E, because A is the peak point, let's say. Okay. Now separately draw the graph of f prime x. So this graph will have what kind of a nature? That at A, its value is 0. Okay. After A, its value is negative. And before A, its value is positive. So it has a decreasing nature.
Understood. Yes, sir.
Okay. So you can see. So at this
So
point,
one
the slope of the
need to note
tangent.
this down.
So this slope is actually what? It is second derivative. Whereas this slope was first derivative. So at a point where the function peaks, the first derivative or rate of change of the function is 0. But the second derivative or rate of change, that is negative. Because the rate of change itself is changing behavior like this. It is going from positive to negative. So it's decreasing. The rate of change is decreasing. So its rate of change or second derivative should be negative.
Sir, can you please repeat this once more?
Yeah, I'll repeat this with an example. Okay, just make a note of this. I'll repeat this with examples. Okay. See, what is the derivative of a function in general? It's another function. Like derivative of x cube is 3x square. So 3x square is also a function.
Yes, sir.
Yeah. Now, what is the behavior of the derivative at the point where we have a peak? Just before the peak, it is positive. Just after the peak, it's negative.
Yes,
You know?
sir.
So that derivative is decreasing in nature.
Yes, sir.
तो उसका rate of change कैसा होना चाहिए? Negative होना चाहिए.
It's decreasing. So yes, sir.
है ना? So the derivative's rate of change should be negative, na? So what is the derivative's rate of change? Is the second derivative?
Okay, sir. But then, first one. Got it, sir.
Well, yeah, Abhinav, you had a doubt, beta?
Sir, at a local minima point, the double derivative will be positive, no?
It will become positive. उसका opposite behavior हो जाएगा, है ना? Because it will go from negative to 0 to positive. है ना?
Yes, sir.
Okay, yeah, Nishchay, you had a doubt, beta?
Yes, sir. Sir, suppose the graph is so rapidly changing that at every delta x, there is a turning point, not a straight horizontal line, but at every delta x, there is means at every delta x,
See,
it is changing rapidly.
that is why, na, Nishchay, we in the proper definition, na, we have to introduce immediate neighborhood. Just neighborhood is not good enough. No, so we have to take x equal to a plus minus delta x, where delta x is tending to 0.
Okay, sir.
Okay, so that is where maths becomes a bit of a like abstract subject, na, that between any two real numbers, there are infinite real numbers.
Yes, I got it.
Got the point? No? So the extreme case of that in fact becomes the this thing, na, that's the constant function. Because on the constant function also, on the x-axis, if you take any two real numbers, no matter how close they are, there are infinite number of real numbers in between.
Yes, sir.
But again, see, we need not worry about those kind of extreme cases. We are more concerned with, natural functions like algebraic functions, polynomial functions, trigonometric functions. So you'll always see that if we take a reasonably small value of delta x, it will fit into this definition of delta x tending to 0 also.
Yes.
And I'll show this with examples also. It will become clear. For example, if you just take sine x, okay, and you're looking at the peak point at x equal to pi by 2, or if you're looking at it in degrees, you can just compare 89 degrees, 90 degrees, and 91 degrees, and it's good enough. But suppose you're taking a function which is like, sine of like 100 pi into x. Okay, so that will reach pi by 2 at x equal to how much? 1 by 50? Sorry, 1 by 200, because I'm taking 100 pi into x.
Yes.
So then you have to take your range of values quite a bit smaller. You have to take the consecutive points, you cannot just take reasonably small values. You have to take quite small values. Okay, so let's first understand the definition of local minima according to this, then we'll come back to this. Okay, so now you can see that at a local minima point for a given function, so suppose the function is dipping at this point B. So we draw a tangent here. It's having slope equal to 0. But we draw a tangent at a point before this, having negative slope, and we draw a tangent at a point after this, having positive slope. And the exact definition, we want to bring these two neighboring points to the immediate neighborhood. So delta x should be tending to 0. So that, this could be a very rapidly changing function also. But even then, this point will be defined as a local minima. This point will be defined as a local maxima. So I have to take the immediate neighborhood. So both of these, I'm taking delta x is tending to 0 and it is a positive quantity. So you can see the behavior of f prime x. At x equal to b's neighborhood is that it is decreasing. Sorry, it's increasing. Okay. So that means its rate of change should be positive. So again, if this is a functions graph, then when I plot the derivative of the function, the derivative should have this kind of a nature, that it is going from negative to positive. This has an increasing nature. So this slope should be positive here, whereas this slope is 0 here. Okay, so this. So now you can see that this is how a local maxima point is different from a local minima point.
Sir, these are curves, and I know it won't apply to this example that I'm asking for, but suppose there's a straight upward going graph and then suddenly it becomes zero. So it was never decreasing, it was increasing, but then suddenly it became zero.
So you have something like this, na? It becomes flat.
Yes, sir.
So you will see that there is no point that satisfies either of the conditions. Okay, because you can see that at this point where it's become flat, the derivative is zero continuously, no?
Yes, sir.
Okay. So what about second derivative? That will also be zero.
How is it zero?
Because you see, if this is a point, let's say x equal to c. Now you plot the slope at a point before c. That's also zero because your line flat हो गया.
Yes, sir.
उसके बाद भी zero है.
Yes, sir.
So now think of how the derivative is looking on the graph. It's a continuous zero line, no?
But sir, in the curved graph, you took so much space. You took the whole thing in consideration. So here, why won't you take the upward slope in consideration?
So because see, then I'm talking about a point over here, no? Okay. But at
No,
some stage,
that's why I was saying it's not a curved graph. It's like a straight and horizontal line.
that is like a broken function, no? It's like you have some curve up to a point, okay, and then you have the horizontal straight line. Okay. So in mathematics, this type of point is called a corner point. Okay. So corner point cannot be defined as a point of local maxima or minima in that sense.
Okay, sir.
You know, because it doesn't have a curvature, no? It's it's a sharp corner. So yes, sharp corners present a problem when we apply this analysis. You understanding the point? Because on one side of the sharp corner, the behavior is different. On the other side, the behavior is different. Okay. Now I'll give you another example. Now you know mod x now. You know the function mod x.
Yes, sir. Yes.
Yes, sir.
How it is defined? It is defined as x equal to 0, y is equal to 0, x equal to negative values, y is equal to minus x, and x equal to positive values, y is equal to x. Okay. So how the graph of this function looks? It looks like a V, na?
Sir,
You
y is
understand?
equal to plus x, right? X is negative because it's
नहीं
upward.
देखो अभी x का वैल्यू में -2 सब्स्टिट्यूट करूंगा तो मैं क्या लूंगा माइनस ऑफ -2 ना.
हाँ.
You understand ना? So when we remove the mod sign na, for negative values of x we have to take negative of that value.
अच्छा हाँ.
Whereas for
Minus of
positive
minus.
values of x we have to take that value only. You know? And at 0 we can take it as 0 only.
So y in that sense will always be greater than 0, right?
Y will always be greater than equal to 0. Okay. So basically, you can see in the negative part of the domain, what is the equation of this line? Is the line y equal to minus x? But you're taking only one part of that line instead of the whole line. Whereas in the positive part of the domain, you're taking y as this line. You're taking it as a part of this line, which is y is equal to x. So that is why the domain is, that is why the definition is like this. That for positive values of x, it is actually the graph of the straight line y equal to x. For negative values of x, it is the graph of the line y equal to minus x. So it is actually not a single function. It is constructed out of two different functions. So it presents a problem for us at this corner point at 0. Now you'll see this point 0, visually it looks like a local minima, right? Because it's a dip point. But it will not satisfy any of these conditions. Because it's not a natural function, it's an artificially constructed function. So it has a sharp corner. Okay. So at the moment, in our definition of these things, we are excluding these kind of situations where there are sharp corners and all. They are, like you can say, exception to the rule, and we'll come back to that. Yes, Nishchay.
So, but if we draw a slope to this point, we will get a 0, right? dy by dx at 0 will be equal to 0.
नहीं आएगा ना बेटा, क्योंकि वो define कर ही नहीं सकता हूँ मैं फिर. Now you apply the fundamental definition of differentiation, na? That limit wala definition. You understanding better?
क्यों नहीं आएगा एक बार आप बताओ.
You apply this definition, na? You can see you will not get it. This is f of x plus delta x minus fx divided by delta x. Okay.
Yes.
Limit delta x tending to 0. Now you take the point x equal to 0, and if you take delta x as a negative quantity, you will get this f prime x as minus 1. If you take it as a positive quantity, you will get it as plus 1. But no way you will get it as 0.
Yes, sir.
So we say that in such a case, the derivative is not defined at x equal to 0. So when you study advanced calculus, now you will see that there is something called differentiability of a function. Just like there's something called continuity of a function. Like the tan x function is discontinuous at x equal to pi by 2. No?
Yes.
Like that, the mod x function we say is non-differentiable. That means we cannot differentiate it, or we cannot define its derivative at the point x equal to 0. Because to the left of it, the derivative is minus 1. To the right of it, its derivative is plus 1. Are you following the point, Beta?
Yes, sir.
Okay. But like as I said, these are very extreme cases and we need not bother about them right now. First, let us get used to the everyday meaning of local maxima and minima. Then we will come to these kind of exceptional cases. So what I mean by everyday meaning of
-1 and 1, right? So in between we have a 0, that is the turning point. And at that,
but मैं definition से 0 कर ही नहीं सकता हूँ ना बेटा उसको. See, when you go with the proper mathematical definition, what is derivative? It is that limit delta x tending to 0, f of x plus delta x minus fx, that one, ना?
हाँ sir.
तो वो तो define ही नहीं हो पाएगा ना. Just like, can I say that tan of pi by 2 is infinity? That's not correct, na beta? Tan of pi by 2 minus delta x tending to 0 is infinity. But then pi by 2 plus delta x tending to 0 is negative infinity, na?
Yes, sir.
So there is a problem in mathematics, na? When something switches across a point like that, we cannot define it at that point, na?
Sir.
Okay. Okay, now let's come back to this. So what we have understood so far, let's summarize that given a function, okay, if f prime x is equal to 0 at a certain point, okay, then what we can conclude that that is a turning point. Okay. But further, if f double prime x is positive, then what that means that that turning point is a which type of turning point? It is a local minima. Okay. And if f double prime x is less than 0, then that turning point is a local maximum.
Sir, but for y equals x cube and x equals 0, f prime x is 0, but that is not
f double prime x is also 0. So it is neither local maxima nor local minima. You understanding my point, Beta?
But I don't.
Okay. So before we come to some situation like this where neither of these two is happening, let's look at a case where at least one of these two is happening. Okay, so let's take the example we had today earlier. We had x cube minus 3x plus 2. Now what we had analyzed from the behavior of the function, we had analyzed that the function was increasing in this part, okay, decreasing in this part, and then again increasing in this part. So if we went with this and went on to draw the graph of this function, you would have seen that the graph of the function something like this. So this would have told us that the local maxima occurs at x equal to -1 and the local minima occurs at x equal to 1. But that is a graph method. Now let us apply this local maxima and minima method. So we want to find the local maxima and minima of this function. So let's do that. So what we'll apply is we'll apply this concept that given the function, first find the positions where the derivative is 0. So you are locating the turning points. Okay, now there might be no turning point, there might be infinite turning points, there might be one turning point. It all depends on the nature of the function. Okay. Then depending on whether you have found turning points and what those turning points are, check the value of second derivative of the function at each of those turning points. If at a given turning point, the second derivative is positive, that means that is a which type of turning point? It's a local minima type of turning point. If the second derivative is negative, what it means that it's a local maxima type of point. Okay, so let's do this now without referring to the graph. So forget about the graph for a moment. Let's do this using derivative and second derivative. So let's say I have not analyzed the number line, I have not analyzed the graph and all that. I just want to from the formula of the function, I want to find out local maxima and minima. So forget about how I've drawn the graph, the behavior of the function on the number line and all that. I just want to do this. Okay. So what is the derivative of the function? F prime x is 3x square minus 3. And what is the second derivative of the function? It is 6x, right? Okay. Now the first thing, find the turning points. So turning points definition, what it was the points where f prime x is equal to 0. So in maths language, we can say it is roots of f prime x. Roots of an equation are the values of x for which the equation's value becomes 0. Okay. So f prime x is what it is, 3x square minus 3. So roots of this equation x minus 1 into x plus 1 are x equal to 1 or x equal to minus 1. So these 2 points collectively are our critical points. So we will say that the function fx has 2 turning points, x equal to minus 1 and x equal to plus 1. Okay. Now next thing what we will do the what is called the second derivative test. Okay. Check f double prime at each turning point to classify it as local maxima or local minima. Okay, so what is second derivative? It is 6x. Yes, Nishya.
Sir, so in this question, we have the information that there are only there is only 2 turning points, right? One of which
so
is
it is
local
logical
maxima
that one is local maxima and one is local minima, right?
Yes.
And the bigger one should be maxima, the smaller one should be minima, right?
Yes.
Okay. So in this function, that logic will work. But going back to my earlier example of x plus 1 by x, that logic will fail. Understood, no?
Yes.
So we have to be a little bit careful. Yes, you can say, okay, this is a polynomial function. So it has a natural curve without any discontinuity. So I can say logically, yes, that if I have 2 points, one is the local maxima and one is the local minima, obviously maxima pe value zyada hoga, minima pe value kam hoga. But suppose I had a power 5 function, okay, then it would have how many turning points? It could have up to 4 turning points.
Yes.
So how do I know which one is the maxima, which one is the minima? No? Because my 4 turning points could be like this. I mean, I've drawn more turning points here. Okay, so this is one where I've drawn 1, 2, 3, 4, 5, 6 turning points. You know? So this is a power 7 polynomial. So how do I know which one is the local maxima, which one is the local minima? So that is where second derivative test becomes compulsory.
So in general, if we talk about a polynomial of degree n, then we can say that the total number of turning points are n minus 1. Can we say that generalized?
Yes, matlab up to a maximum of n minus 1, might be less than 1. You understanding? No? I can have a cubic function which when I differentiate it, it's a quadratic function that does not have roots. So then there is no turning point. Or it could have one common root.
Yes.
So polynomial of degree n will have up to n minus 1 turning points. It can have anything from 0 to n minus 1 turning points. So cubic function may have 0 turning points, may have 1 turning points, or it might have 2 turning points, but it will not have more than 2 turning points. Yes, Mansi, that's the same thing. Like checking the sign of the second derivative is equivalent to checking the concavity. Na? So at a peak point, it is always convex upwards. At a dip point, it is always concave upwards. So they are interchangeable things. Na? Saying that second derivative is positive is interchangeable with saying that it is a concave upwards point. Okay. So you can say that yes, this step, the second step, is equivalent to checking the concavity of the graph. Okay. So now we need to check each of these. Okay. So you can see that second derivative of the function is 6x. Therefore, at x equal to -1, f double prime of -1 is how much? -6. So f double prime is a negative quantity. Okay. So that means it is a point of
Local maxima.
yes, it is a point of local maxima. Okay. It is not the local maxima. It is the point where the local maxima occurs. Okay. Because the local maxima is the y coordinate of the graph. And at x equal to +1, f double prime +1 is +6. So x equal to +1 is a point of
Local minimum.
local minimum. Okay. So now the function was x cube minus 3x plus 2. So we can say that local maxima equals to f of 1. Oh, sorry, f of -1. So that equals to how much?
-2.
No, -1 plus 3 plus 2, no?
4.
Plus 4.
4.
Okay. At which point? At x equal to -1. And
So is it important to write at x equals to -1?
no, because here it's already obvious no, that it's occurring at -1. So that's why I've written in brackets. No? Just to make it clear. You know, what is the value of the local maxima? It is +4. Okay, so what we've written over here, this is the value of the local maxima. That is +4. But where it occurs, that it occurs at x equal to -1.
Yes.
That is. So just to get the nomenclature clear, you know, what if the question asks you find the local maxima of the function, you will not answer x equal to -1. You'll answer the local maxima is 4. But where it occurs at the point x equal to -1. Okay, this point is clear, people?
Yes.
Yes, sir.
Okay. Similarly, we will say that local minima. Yes, Janvi.
Sir, sorry to say this, but sir, we have classes from 9:40 today.
Okay,
The
so
school.
just write this. I understand. Okay, so let's just wind up. Okay, so that local, so that will become how much? 1 minus 3 plus 2 is equal to 0. Okay, so this is the value of local minima, and where it is occurring at x equal to Okay, yeah, people. So those, especially those of you who have class, you can immediately log out. Okay, others can finish writing this down if you want. And anyway, the class is done. Like we wanted to discuss up to this point. Okay.
Thank you,
So
sir.
I'll be sending you an assignment specifically with questions based on local maxima and minima now, and also global maxima and minima. Okay, so we'll look at the whole thing together. The concept of maxima and minima, global and local. Right?
Sir, when will we get the result of the nature test?
I think by today evening you will get it, but you will get the individual results, because this was like a trial test, you know, just to get you used to the website, get you used to the process of taking 3-hour exam with, you know, 2 types of questions, MCQs and integer answer type questions. So there will be no ranking, etc. given in this. It will be just your individual marks. Yes, Nishchay.
Sir, I had some doubts from the paper. Will you discuss them now or?
I think we have a session for the discussion of the paper this week, right?
Yes.
Your time
Yes,
yeah. Okay. So we'll do the discussion of the paper during the session. But in the meantime, if there's some question in which you want some hint and all that, you can just send it by WhatsApp to me.
So you will not be taking that session, right?
If I actually don't remember the timetable, like who is in which session. So it may not be me. It will be one of the physics teachers. Right?
Ajit sir is taking it.
Ajit sir is taking, then he will be taking, don't worry. But yeah, if some question you need to discuss with me, you can always discuss with him, no problem. Okay.
Okay, sir. Thank you.
Okay. Okay.
Thank you, sir.
Okay, people,
Thank
that's
you,
it for
sir.
today.
Thank
you,
All the
sir.
best. Yes.
Thank you, sir.
Thank you, sir.
Sir,
Yeah, beta.
can you conduct an extra class? I don't know, personal or however you'll do it, for word problems of differentiation.
Okay, we will do now. We'll do some, like, you know, when we complete this differentiation topic fully now, we will do some revision questions. In that, I will do some more examples of word problems. Okay.
Okay, sir.
Okay. In any case, we will do discussion of exercise 3 and similar problems. So we'll do word-based problems.
Okay, sir. Thank you.
Okay, beta.
Thank you, sir. Bye.
Okay, bye, people. Bye.